dy squared plus 3dc squared. I mean, whatever you start with here, you can end up with something different. I can start here with maybe x squared plus y squared, whatever. You can start with something different. But if you start with the standard one, you will get some g, the standard g. The nabla that is compatible with the standard g is called Lec18, covariant derivative. So now the geodesics of the standard g, the geodesics of this guy, they are exactly the same. So if this is the standard one, standard metric, standard line element, and this is the Lec18 covariant derivative, they are compatible. I'm not going to go into these details. We know that they are compatible, means that they have the same geodesics. So the curve that has zero acceleration from this point of view is the exact same curve that minimizes the distance. Okay? Okay, and we get more. What do we get? We get actually two things out of that. First, anybody remembers what was hard here? What was hard? What we didn't cover last time. How to get gammas, right? These were hard things. I just gave you gammas. Because gammas have to satisfy very strict conditions we didn't even talk about, but this whole thing that is xk dot dot plus gamma ij k xi dot xj dot, this thing has to be tangent. This is very hard to achieve. At any rate, well, if they are compatible then, and this guy is very easy to get like we did this time, then there should be a way to get gammas from the g's. And indeed, yes. If they are compatible, this is in general with any two sets that are compatible. The gamma ijk is equal to 1/2 summation over L from 1 to n gkL times partial g I L partial xj partial g jl partial xi minus partial g ij partial xl. I'll tell you how to do one of these, but it's really tedious. But that's fine, at least it gives you a way to get the gammas. We'll have some training on this relation now. But here is a relation. If you have the g's, your matrix, which is very easy to get, actually, we got it today. If you have your g, then here is the formula to get your gammas. That's good.
So it's g to the power k?
KL. What else do we get? Well, you know, here the geodesic, the straight line is not completely defined. It's just say that, well, please solve this calculus operations problem to get your straight line, right? This is already solved here, and we know exactly the equation. So now the geodesics indeed satisfies this equation. Give you some time to write. And then we can have a little bit of training on this formula.
So what's this second part? Is it g?
What's second part? This one?
No, the other one.
This?
No, the other one. Yeah, this one.
This is the equation of the geodesic.
The endpoint of that calculus of variation solving problem.
Yeah, I don't need, this one saying is that I don't need to solve this calculus operation problem anymore, because if the geodesic coming from here is the exact geodesic coming from there, well, here is an equation governing the geodesic, right? So you can use it readily without solving the calculus operations problem.
So you find the geodesic, either Riemannian metric, then you go to the other side, and then you calculate.
Very good. That's right.
Question?
Yes?
In the statement you said if nabla and g are compatible, but is it a general case that they are would be?
No.
It's only.
Not any nabla and any G are compatible. But you can say, given a G, I can look for the nabla that is compatible with it. So the standard G, the one that's compatible with it, something called Levi-Civita connection, or Levi-Civita covariant derivative, whose gammas, remember any nabla is defined by the gammas. So this guy, whose gammas are defined in this way. Okay?
So where does the mass go?
What?
The mass properties. We took the mass and the radius to be unity.
That's fine. You can always retain them. They don't
matter.
the mass don't matter for a free particle, indeed, right? It will not be the case with general relativity. We're gonna know why. But if you have a huge mass rolling over the sphere, it will have the exact same trajectory as just 1 gram, right? It doesn't matter. Correct? Yes, please. It's the same trajectory. Yes.
The gamma you found here, is it only applicable when nabla and G are compatible?
Yes. So everything above this line is general for this guy and this guy. Now, if they are compatible, then we got to make use of this. Okay? Geometry of mechanics. What is the geometric point of view of mechanics? Is that our configuration lives in a manifold, right? Curved space. Our velocity lives in the tangent space, right? Correct? Our kinetic energy Mace matrix Q dot, our kinetic energy is simply a Riemannian metric. On this manifold. Why? Because it takes two velocities and gives you a real number. What is the matrix? The matrix G of the Riemannian matrix is simply the Mace matrix. So this guy is the G. This is your G, right? That takes any two vectors and gives you a real number. First vector transpose, the second vector as a column. Here is your G. So your kinetic energy represents a Riemannian metric on your manifold, on the configuration manifold, right? Okay. The equations of motion are such that what? Well, the principle of least action say that the first variation of the integral of t dt is 0, right? So the trajectories, let's say, trajectories of the motion. Trajectories. From the principle of least action, we know this from before, long time before. The first variation of the action integral, which is simply the integral of the kinetic energy, should be the Lagrangian if we have potential energy, right? This is 0. Indeed, this is equivalent to the first variation of my Riemannian metric, right, which is again T. G of Q dot and Q dot, this is simply T, right? dt. It's the exact same equation. The first variation of this guy is 0. We are minimizing this guy. So indeed, my trajectories are geodesics, right? They are straight lines, whether they are curves with 0 acceleration, whether they are curves with shortest path. Okay, this is the principle of least action. This is just minimizing the distance on a manifold. If the manifold is our configuration manifold, and the Riemannian metric is our kinetic energy, then this statement is exactly equivalent to the principle of least action. Okay? You have any question about this? I mean, this is the the questions in the homework exam will be very, very straightforward, but what I want to really care about is this conceptual thing. So if you didn't grasp it, you are very welcome to come up with questions, please. I know that for sure it's not easy to grasp it. The next board will be the general relativity, which you know that not everybody in the world understands the relativity, right? So I know it's not that straightforward. It's not that straightforward. But it's indeed beautiful concept where dynamics, calculus of variations, and geometry beautifully come together, right? This line includes the three dynamics, because we're talking about how things evolve in time trajectories of bodies, right? Particles. Calculus of variations and geometry. The three come together in a unified principle. You have a question about that? Any question, please?
Could you please explain the green line once more?
Yeah, sure. How we derive the equations of motion from mechanics in this course? Lagrange's equation, right? And what's the origin of Lagrange's equation? Is that the first variation of the action integral is zero, right? The action integral is the integral of the Lagrangian. Now we're dropping the potential energy for a moment. So it's simply the integration of the kinetic energy. So this guy gives you Lagrange's equation, right? This is Hamilton's principle, principle of least action, Hamilton's principle, right? And here, I'm just concerned with the shortest distance on that manifold. It happens to be, I selected my configuration manifold to be the manifold under study. On that manifold, I can specify many Riemannian metrics. I particularly chose the kinetic energy to be my Riemannian metric. So if you're concerned with this configuration manifold and this Riemannian metric, then the shortest distance here is the statement of the shortest distance, right? We're minimizing this integral. This is the length, right? Or you have just the square root to get the length. So we're minimizing the length, which means the first variation is zero. So the statement of the shortest length is exactly equivalent to the statement of the principle of least action. Both invoke or use calculus of variations for sure, because we're minimizing functional. Okay, like I promised, we need to do a little bit of practice on this, and I'll immediately jump to special relativity, one line, general relativity, couple of lines, and we're done. So we need to do practice on this. So I will erase everything here except this formula. Anybody needs anything from this board? Okay. Okay. So given G, I want the gamma G's, right? Anybody has a problem deriving the G on your manifold? You can do it now. I mean, you have this equivalence between dynamics and between geometry. So if I'm given a surface, I can start. I'm given a surface and I want its G, Riemannian metric, standard Riemannian metric. What can I do? Well, I can do many things. First, I can start with this guy, the standard line element in Euclidean space, which is dx squared, y squared, z squared, and substitute by the x, y, and z in terms of my coordinates, like here, and just expand it. I'll immediately get my G. There's one thing. What's the other thing? You consider as if there is a particle of unit mass evolving on that surface, and go and compute your kinetic energy from pure dynamics perspective, right? And then write down your kinetic energy as velocity transpose mass velocity. This is indeed your G, right? You can do it either way, whatever you're comfortable with. Maybe you're more comfortable with the dynamics aspect, because we had a lot of training on kinetic energy, whatever the surface that you have. So start, position vector, velocity vector, right? Kinetic energy, and then expand the kinetic energy as Q transpose MQ. You get your mass matrix, which is the Riemannian metric G, okay?
What
Yes.
if we have potential energy as well?
We'll talk about potential energy in a moment. But the Riemannian metric is just is only with the kinetic energy anyway. Because when I ask you about Riemannian metric or a manifold, this is pure geometry. I don't care about dynamics. So we're not talking about dynamics. I'm saying that, okay, I can solve this problem by equivalence with a dynamics problem rolling on my surface, and there is no gravity. Okay? So if you start with this G now, I start with this G. Here is my G, which is cosine squared phi 0, 0, 1. And I need to get the gammas. This is 2 degree of freedom system, so you have 2 gammas. Gamma, so the objective, the end objective is to get 2 gammas. Gamma theta and gamma phi, which I magically gave you last time. This was, if you remember, 0, negative tan phi 0, and this guy was sine, cosine, zeros. The gammas do not have to be symmetric, but this guy for sure has to be symmetric. G is a symmetric and positive. So from G, I want to get these 2 gammas, okay? This is the goal. And here's the formula, just applied verbatim, that's it. Just be careful when you apply, and that's it. The only thing that I need to point out is that when we have the indices as superscript, not subscript, then we're talking about the inverse of the matrix. So this guy indeed is G inverse, the entry KL of it. Okay, that's it. Okay?
Why?
Well,
I understand it.
oh, this is the way of writing it. So when I write GKL here, what we mean is the inverse of GKL. Okay? Which means that you need G inverse. So let's get G inverse, please. So G inverse is, this is a 2 by 2, so it's easy, and you'll always, I mean here at least, you'll have 2 by 2. So how you do it 2 by 2? Anybody remembers?
Determinant
Yeah,
of work.
first the
Yeah, you swap these guys, and you do negative on the offside, but they are zeros anyway. And don't forget to divide by the determinant, please. The determinant is cosine squared phi. So this is 1 over cosine squared phi, 0, 0, and 1. Okay? I mean, and it's a diagonal matrix. You could have done it easier, right? If you have a diagonal matrix, just invert each element. So this guy is 1 over cosine squared, this guy is 1 over 1. But if it's not diagonal, this is how we do it. Swap and change the sign, divide by the determinant. Okay, you got your G inverse. I'm going to apply this formula verbatim. These are all G's, but this guy is G inverse, okay? So I'm going to do one. Maybe let's do gamma theta, this guy. So